Okay, thank you very much for being with us. We are very delighted to have many people registered for those webinars, and the one on Airborne particularly dear to my heart because I will always remember the 250 scientists who petitioned for the WHO to recognize that those scientists made a petition so that the WHO would recognize that COVID-19 was airborne. And it is only this year in 2024 that actually some of the best scientists on that team were called upon by the WHO to do a report admitting that COVID-19 was airborne. It is, I think, a very, very important topic for AMR, but also for other diseases. And I want to thank particularly Tim Walsh for being with us, Yuguo Li, whose work followed since his remarkable work on SARS-1, the 2003 epidemic, and Professor Xiang-dong Li, who was introduced to us by Tim, and who is also a remarkable figure in the world, the limited world of experts on airborne transmission of diseases. I was in your city in Hong Kong in 2019, and I loved it. If I could, I would have settled there. So I hope I get the opportunity to go back to Hong Kong, and I hope you all three will have the opportunity to come with us in Dubai for an in-person conference. With that, I think Professor Jim Walsh, you can introduce yourself. It's the best, but you are so famous in AMR that you don't need that much introduction. Thank you.
Thank you, Gareth, and thank you also to the other speakers. So, good morning, everyone, or good evening, depending on where you are in the world. My talk that I was given is on airborne vectors, and particularly things like flies and cockroaches, and I think the importance of them and actually the enormity of them. At the top of the screen there, you'll see that I'm director of Barnard, which is still an ongoing study looking at neonatal sepsis in various countries, particularly low middle income countries. And my affiliation on the far left is with China Agriculture University, which I have an honorary chair, and still do a lot of work in China, which has, despite the sort of the geopolitical climate, is something that I think is extremely important. And I would just add to that point that 2024 has been a very important year in the realm of antimicrobial resistance. We've had the UN high-level meeting in New York in September, and there was a finance meeting just recently held in Jeddah in Saudi. And, so therefore there is a lot of kind of energy, if you like, being applied in that area. And I think, despite the geopolitical sort of climate, I think actually that China has a very, very strong role to play in the governance of this, but also in the research and the technical tools available to answer some of the research questions, which I'll allude to briefly in my talk. So can I have the next slide, please? Great. So this is quite easy because I think this has been converted to a PDF now. So I think this is sort of an introduction, not just for my talk, but also for the other speakers too. And the one thing that we have is the confusion with the language. COVID was kind of easy, and COVID was like an earthquake that hit. And we often refer to AMR, well, as the silent pandemic or as the slow tsunami. And that's also kind of, whilst it is true, it is slightly unhelpful, because if it is slow, then nobody really cares. And when will it hit us? And so that is also, not necessarily a useful analogy. AMR itself is very confusing. What does it actually mean? And I think that sort of confusion has been further exacerbated with sort of terms like One Health or quadripartite, so we sort of add these sort of acronyms or terms on to something that is actually to do with the bacteria, and everything's to do with the bacteria. Antimicrobial resistance is fundamentally about the bacteria, the bug, and how it becomes resistant to antibiotics, and everything else is sort of just terminology that we put around this fairly simple concept. So I think we have a problem in terms of language. And AMR is very complex. It's not like COVID. COVID was a one bug, one disease syndrome. And actually dealing with COVID was reasonably simple once we knew exactly what it was and how to manage our patient population, and also about transmission events as well. With AMR, it applies to all bacteria, both friendly and pathogenic. And then dealing with the whole realm of bacteria is really, really tricky. I worked out that there's something like about 10 to the 20 antibiotic resistant genes in chickens alone on planet Earth. And that number is just phenomenal and frightening. So we're not going to actually deal with this. We're not going to win this battle. We just have to think about how we manage everything going forward and how we conduct studies to try and understand better the dissemination of AMR. Can I have the next slide, please? So, as I said, antimicrobial resistance starts fundamentally with the bacteria, and actually it's the antimicrobial resistance gene. Now, here I've put what we would call not intrinsic, but acquired resistance. In other words, the bacteria, the recipient, has a new resistant gene. We call it an ARG, antimicrobial resistant gene. And surrounding that are usually other antimicrobial resistant genes, and we can talk about collateral damage and co-selection. But around that sort of complex, which may involve one gene, or it may involve 5 or 6 or 7, you have sort of a plethora of mobile genetic elements. And these are very important because they mobilize the antimicrobial resistance genes. We have things like transposons, we have ISCR elements, which we discovered and named about 15 years ago, which are very, very important and quite frankly ubiquitous throughout all bacterial populations, certainly in gram negatives. Things like ISAs, integrons, which are usually associated with transposons, but not necessarily, and just IS elements. And the most common one that most people will know will be IS-26. And so you have these genes that are able to mobilize large sections of DNA. And then what will happen is you will then have homologous recombination. And a homologous recombination can be the rearrangement, the movement of reasonably large sections of DNA where they can be either inserted into the chromosome from the plasmid and from the plasmid into the chromosome and vice versa. And so we have this sort of moving always. And a lot of people think about bacteria when we sort of isolate them as being very static systems. They are not static systems. They actually, the bacteria, the DNA in the bacteria moves. If anybody's seen an aurora at night, you will see the sky move. And that's actually, I think, very much what a bacteria does in terms of its DNA, either with SNPs, in other words, single nucleotide polymorphisms, where you might actually change expression, but also mobile genetic elements moving DNA within the particular bacteria. Then outside of that, we have conjugation. And I'll talk about that in a moment because that's very important, how the bacteria is able to move large sections of DNA from one bacteria to another. And that will then involve things like stability, toxin, antitoxin systems, fitness, and compatibility. And the way in which we've kind of got our head around kind of the mobility of plasmids recently has opened up a whole series of questions about the range of plasmids. Before, it was just very much a cultural to cultural based system, and then we've moved away from that. We're using a non-cultural based system, which has just completely blown our mind as to how widespread plasmids can go, and they can cross the gram positive, gram negative barrier and vice versa. And we never thought that was possible before, even with common plasmids like, for example, INCEX3. And then outside of that, if that wasn't complex enough, we then have the various sectors, animal, human, and environment, that we then have to deal with. So when we consider the whole realm of antimicrobial resistance, it is very complex. It is not like COVID. And I think to all comparisons with COVID, or even with Mycobacterium tuberculosis, TB, I think is not very helpful, because it is a lot more complex than what we had first, was just a lot more complex to try and describe to the layman person. So we've got to dampen down the language, but it is complex. Next slide, please. So this is kind of just adds to the complexity of everything. We have more bacteria in us and on us than we do human cells, and that also applies to other animals. And so we're coated in these microorganisms, and we have anywhere between 10 to the 12 and 10 to the 14 bacteria per gram of feces. So when we defecate and animals defecate, the bacteria go everywhere, and a lot of those bacteria are full of antimicrobial resistant genes. And so we have to think about how we manage our waste, and particularly in the light of increasing antimicrobial resistance, which may or may not be directly associated with the consumption of antibiotics. So also with that, how we actually manage biosecurity in the future, and what animals are likely to harbor more antimicrobial resistant genes than others. We're very much dependent on meat sources, and that I think will continue. And it also really, I'm not entirely sure the argument that we should all become vegan or vegetarian is going to help necessarily the matter, because we still will be reliant upon antibiotics to manage crop diseases. Certainly, if you look at greenhouse gas emissions, actually chickens are much better than pigs, and also certainly beef, as you might imagine. And also the poultry sector is forever expanding because of value for money, for the amount of energy you put into the animal, but also for faith-based reasons, where not all societies, for example, will eat pig. And so, thinking ahead how we actually manage this and how we use antibiotics across both human and animal sectors is very, very important. And then we have to think about how we look at wastewater and potable water, and how we separate them, particularly with the increase in climate change or temperatures associated with climate change, which will exacerbate the problem even further. Next slide, please. So where do we put our resources in all of this? And, we can put it into hospital infrastructure on the far left, or, we can then put our money, if you like, into novel antibiotics. And, but in between all of those, there is things like diagnostics and IPC. The IPC can apply to a hospital, but it can actually also apply to, for example, a large farm, an industrial complex, where you've got to try and protect the animals from being sick. Antibiotic access is key in everything. And the one thing that we find is that in low-income countries, they will have access to lower grade antibiotics, but when it comes to watch and reserve, those classes of antibiotics often they don't have access to, which is kind of a real problem. Next slide, please. So this is a study that I just really want to quickly run you through. This was a study done in Peshawar and in the Kabir Teaching Hospital, which is a sort of a public hospital. I think it's about roughly about a 1,000-bed hospital, but serves a very large population in Peshawar, along with the Lady Reading Hospital. You can see sort of the environment that, where the hospital is based. Just outside of the hospital, there was a waste ground, a dumping ground, where you had things like surgical gloves, needles, and general hospital waste sort of just dumped out, and that was within a 1 kind of kilometer radius of the hospital. And so you can imagine that sort of flies would go into this hospital very regularly. We came across this idea, I came across this idea about 15 years ago now, where I was in actually Karachi, not Peshawar, and I saw flies going from one baby to another, to another, to another. And I just thought, well, this is crazy, maybe, you know, the flies are carrying AMR bacteria. So therefore we conducted this particular study very quickly. We had 4 wards, 2 female, 2 male. We cleaned the wards thoroughly, and we conducted the study over a 2-week period, and we did, if you like, 2 timeframes, one in the winter and one in the summer. And the picture on the far right was what nature did in terms of the artwork to take, kind of make this sort of live, and it's called AMR on the Move. Next slide, please. So this slide's a little bit busy, so let me walk you through it. This work was championed by Breshna Hassan. And what we've done is to sequence the bacteria that we collected from the surfaces, from the patient wounds, and also from the insects. What was very apparent was actually it was cockroaches that was causing the dissemination of AMR in the winter and flies in the summer. And that sounds pretty horrendous when you kind of think about cockroaches, but they will, you know, in the night feed on wounds. We were able to do sequencing and SNP analysis, and I think our cutoff was roughly 20, but we then also looked at 30 and 50 and so on and so forth. And we found actually that the same bacteria are circulating in the hospital over a long period of time. And then simply what happens is the cockroaches or the flies will pick them up and then kind of infect or colonize the wounds, because a lot of these wounds are polymicrobial. And so we're able to look at various clades, that's on the left-hand side, and using SNP analysis, link actually a cockroach to a particular person's wound or to the hospital service. And very quickly, the hospital service became contaminated after we cleaned it thoroughly. The slide, well, sorry, the figure on the right, it just shows you the level of resistance. And you can see that this is across species. E. coli was the most common one, Enterobacter and Klebsiella. And you can see that we have very high level resistance to 3rd generation cephalosporins and pretty high level of resistance to antibiotics like aztreonam and also to carbapenems, ciprofloxacin. Fosfomycin seems to be quite active still, ticacycline, and also colistin, which is sulfate, which is actually on the far right of the figure. Next slide, please. So what does all this mean? Well, basically, if you sort of work out, you know, just from our study, which was a single, well, double point snapshot study, roughly 20% of the flies and the cockroaches. We also looked at spiders and moths and ants, but cockroaches and flies were the dominant species. In terms of the cockroaches, it was Blattella germanica and Blatta orientalis. And in terms of the flies, the main one was Domestica mucus, which is very common in that area, and in fact, actually pretty much ubiquitous throughout most countries. 70 to 80% of them carried, the bacteria carried ESBL. And if you kind of look at the figures and the models, and I'm not an expert in this, but roughly there's 17 to 18 million flies on planet Earth to every human being, which I find extraordinary. But that number will increase with climate change. And so then if you sort of do the maths, you know, by 2080, roughly speaking, 50 trillion flies will be carrying carbapenem resistant bacteria. Now, let's suppose we're wrong. Let's suppose that we are out by a factor of 100. You know, that still means 500 trillion, you know, we'll have, you know, bacteria will be carrying antibiotic resistant genes that mediate resistance to carbapenems. And so, you know, the numbers are huge. And so this sort of sector is really, really important in terms of spreading resistant bacteria. We can't say necessarily disease, but resistant bacteria from one sector to another. Next slide, please. So there's been a lot of interest in this to a degree. It's not like One Health, where the interest in One Health has literally shot up through the roof over the last 10 or 15 years. Most of the studies and the research done in this area is trying to isolate antimicrobial peptides from cockroaches or from flies, and not necessarily as vectors of spreading antimicrobial resistance. And so there's a review there that I'll put on the left-hand side of the screen, and you can see that the publication rate has sort of tailored off a little bit, over the last couple of years. But actually, interestingly, there are not many large studies looking at this. So when we talk about, for example, flies as vectors of AMR, we're talking about the probus, are we talking about the wings, are we talking about the feet, or, are we talking about, the gut itself? When we've done our studies, we haven't discriminated between those particular sectors, because when the fly actually lands on the patient, for example, whether it defecates, whether that gets on the wings or the probus, we haven't made that distinction, and we don't necessarily think that's necessary either. Next slide, please. So this is a study that we did where we're looking at carbapenem resistant bacteria that were carried by flies in China. This just shows you the methodology that we've done. It was very similar to what we did in Pakistan, where we actually capture the flies and then we mash the flies up, and then we will either grow on selected agar, and then we might do PCR. There's various ways of going about this, or you simply extract DNA from the actual fly itself or the cockroach itself and do PCR or genomic sequencing on that. What we try to do with the genomic sequencing is kind of specify that to the bacteria that grows, otherwise it will get a little bit messy. But you can look for carbapenem resistance, you can look for colistin resistance, you can look for tigacycline resistance. Once you set up this model, it's fairly straightforward. Next slide, please. So this is what we found, and I just want to highlight 2 points here. First of all, again, we are focusing on carbapenem resistance. Why was that important in China? Because China has a big NDM problem. It's not KPC and it's not OXA, but it's NDM. And as everybody probably knows, NDM was first discovered, or the origins of which come from South Asia, probably India, but somewhere in South Asia. You can see that NDM1 and NDM5, and they are the big players in this, which is very, very typical of what we will see throughout the whole of this particular region. But you'll also notice that in A, where we've looked at human communities, and B, where we've looked at farm environments, that it is Providencia, the bacteria Providencia, that carries most of the resistant genes. And there's a reason for that, because Providencia produces chitinase. And chitinase is an enzyme that is able to kind of break down chitin, which is, if you like, the shell of the fly and I guess the cockroach as well. And so there's an association of Providencia with vector-borne antimicrobial resistance. Next slide, please. So these are just the resistant rates, and if you quickly look at them, you'll see that actually it's pretty frightening. On the far left-hand side, you have Providencia. You have virtually total resistance, as you might imagine, to all carbapenems, all cephalosporins, and you have high-level resistance to tigacycline, pretty high-level resistance to ciprofloxacin, roughly 51% resistance to aztreonam, and only amikacin is the antibiotic left. You also have a cephalosporin there, kefmetazole, which is not freely available in other countries. As you move from left to right, you can look at the resistance that we find in E. coli and Proteus species and Klebsiella. The scary thing about Providencia, or the the Providencia group, which includes Proteus species, is that they are intrinsically resistant to colistin. So therefore, once they acquire resistant, then obviously you then start to, if you like, have your superbug or your extensive drug resistant isolate. Next slide, please. This was another study done by the same group, where they basically looked at flies again, and this was specific to TET-X. Why is TET-X important, or this particular type of TET-X? Is because it mediates resistance to tigacycline. And so not only do we find in China that we've got dissemination of resistance to carbapenems, but also to tetracycline. This is almost certainly exacerbated by the use of chlor or oxy tetracycline in farms, not just in China, but many other parts of the world. Next slide, please. And this just sort of shows you the provinces where they worked, the various communities, community and farm, a bit like the previous study, and the various species which we found the TETx in, and which interestingly enough was not in Providencia, and also the ARGs. And TETx4 seems to be like becoming the dominant tetracycline resistant mechanism. Next slide, please. This was a slide that was also done by a group in China, again, looking at carbapenem resistance. It's fairly similar, so I'm not going to dwell on this too much to the ones I've previously mentioned. The slide on the left is a skanky diagram. The slide on the left looks at the various types of plasmids, the species of the host bacteria, in other words, the origin, and the various sampling locations. So normally I would go back to front on this, but it doesn't matter. But again, you can see that E. coli is very dominant, but then if you go to the bottom of the middle column, you will see that again we have Proteus and Providencia again being reasonably prominent in terms of mediating this type of resistance. And you'll also notice actually that the plasmid types are at the moment untypable, which is in itself interesting. We have a lot to learn about plasmid types and plasmid biology. Next slide, please. So this is my final study that I'm just going to talk to, and this was some work that we did in Fuzhou. The lady who champions this work, her name is Chua Yang from Fuzhou University. This was different because what we try to understand, and this is using unculturable conjugation, like I mentioned at the beginning. So we take a plasmid and we label a plasmid, and they will take the gut microbiome from the fly, and they will just simply ask the question, where does the plasmid go? And that is very different to a cultural based system because we're not relying on culture. And so we then kind of go into a bit closer to what happens in the real world to try and understand plasmid dissemination without use of culture, or being limited to the use of culture. Next slide, please. To cut a very long story short, this is what we have found. You'll notice that actually Providencia again feature reasonably prominently. They're the ones highlighted in the red down the phylogenetic tree, about 3/4 of the way down the figure on the right hand side. And typically we found that this plasmid would go just about everywhere. It would cross families, it would cross phylum, and it was really surprising. And again, it just shows us how little we understand of plasmid biology. But again, you will see that there is a preference, or at least an association, perhaps we could call it, of Providencia being plasmids going to Providencia, but then also Providencia being associated with the carriage of ARGs. Next slide, please. This, I'm not going to dwell on this at all. This just shows you basically looking at the association, that the relative abundance, and Providencia stewartii was a very common species that we found in, as well as E. coli and Klebsiella. In the interest of time, I'll move on. Next slide, please. So this is kind of where we are at the moment in terms of report from Graham, and I'm not going to say too much about this because everybody talks about these particular studies and also the forecasting of this. But it looks like almost certainly that the burden, I think we can conclude, of AMR will be borne by low-income countries, which do not manage, where flies are prominent because of the temperature and because of probably other climatic issues. And so this really doesn't help. We were talking about AMR, airborne sort of vectors. This will be very prominent in South Asia and Africa. Next slide, please. I'm just showing you this because this is some modeling again that was done by the Graham people, or the Burden study, and what they did was to take 2021, where we are pretty much now, and sort of forecast to where we will be in 2050. And I don't, if you kind of look at the world maps, there is the center. Russia notwithstanding in 2050, there is this sort of center whereby there is an association with AMR, high rates of AMR, with temperature across the equator. I think actually that Africa and South Asia will be hit a lot harder in the next couple of years, not least because of climatic change. Next slide, please. So, how bad will it get in gram negatives? I've spoken about TET-X, which is evident here. I've spoken about MCR, the studies that we've done on that. I've spoken about carbapenem resistance. And unfortunately, airborne vectors, which are often is not invisible to us and not really prominent, certainly in the UK, sort of escape our attention, but unquestionably, as hopefully I have shown you, is that they are should be taken very, very seriously, not least within hospital environments. Next slide, please. So I've spoken about the problem, and I gave this slide right at the beginning of my talk, and I think in terms of hospital infrastructure, there is so much to do with managing fly populations in low-income countries, and a lot of those interventions can be very cost-effective and affordable for low-income countries. Next slide, please. This is from WHO. This is the Sustainable Development Goals, and the one thing that I just wanted to talk about this is the fact that actually flies and insects actually sort of dovetail into a lot of these, into things like food, into things like sanitation, into things like water, and I actually would like to make AMR its own Sustainable Development Goals through the UN. That would be one of my dreams. Next slide, please. The one thing that we can unquestionably say is that when you get destruction of infrastructure and you have decreased sanitation, like they have in Gaza. So on the left we have Gaza, on the right we have Ukraine. I'm being apolitical here, is that we have destruction, you have a catastrophic breakdown in sanitation, no vaccines going into the area, a lack of clean potable water, and obviously flies, because of the sanitation, the defecation and so on, actually proliferate in this area, and they exacerbate the problem. Next slide, please. It's also associated with climate change, I've mentioned at the beginning, where basically you have flooding and you have contamination of potable water with sewage material, and across farms, etc. Whenever you have this breakdown of this infrastructure, again, airborne vectors will spread AMR across many, many kilometers. And I think actually the range of a fly is roughly about 5 kilometers, depending on what fly you're talking about. Next slide, please. This was from the Lancet series, was published in the summer, and I think it's very good, because what it does tell us is that if you want cheap, affordable interventions to actually lessen AMR in low-income countries, WASH is one of the key things to do, as well as IPC and sanitation, but WASH and IPC. With that IPC has to come interventions to manage your insect population within medical environments. Next slide, please. So this is a study. These are my final slides that we've got going on at the moment. So on the basis that we found in Pakistan, in Peshawar, we're now doing a sort of a broad study across the world. I think we've got now about 70 or 80 centers on board. And what we're looking at is mapping AMR rates in particular hospitals in particular countries to the fly population that we actually capture within those hospital environments. I've highlighted the Nigeria and Pakistan here because we actually have intervention studies. What will happen if we put fly traps in? What will happen if we put fly screens in? How much do they cost? What will they do to lessen the dissemination of AMR, particularly in a general medical ward through surgical site infections, kind of preventing the contamination of them? And so this is sort of a follow-up study of what we're doing in the previous study that I showed you. Next slide, please. So this is what we do. These are the countries that we're sort of focusing on at the top there, but we're also collecting data from Northern Hemisphere countries like Norway and the UK and so on. And we have a microbiology platform. We do next generation sequencing. So again, we're looking at SNPs and we're trying to map what we find in the flies to what we actually might find in the patient population to understand just if this is related to temperature, is it related to precipitation? And we also are able to GPS track very accurately where we actually get the flies. So we're trying to assemble this big data set to understand better the role of airborne vectors. Next slide, please. So my conclusions, the role of flies, is varied and complex. One thing I haven't really spoke about is the role of cockroaches. Obviously, we did that in the Peshawar study, but we're not too sure exactly, and also catching cockroaches is a bit of a nightmare, quite frankly, compared with catching flies. Climate change will unquestionably add to this problem and exacerbate the whole dissemination of AMR. And I really do think we need kind of larger studies. A lot of those studies that I went through, which most of them were published this year, are not particularly, large. Obviously, sort of a pan-China study through the good work of Zhejiang University and Rong, but actually I think we need to understand a little bit better sort of the global impact of flies. And there also provides the opportunity for simple and cost-effective interventions. Next slide, please. And I think this is my team in Oxford and who do all the work, and particularly with the work that we're doing at the moment, which is called AVIA. I'd like to thank Kirsty Sands, and I'd like to thank Edward Portal, and we've got a group of PhD students working on this, and they're numerous, so I'm not going to mention them, but a big thanks to the team here in Oxford. And my final slide is to say thank you very much in all the languages from the countries where we work. So I think that's the next slide, please. Great, that is me done. Thank you very much for your attention, and hopefully this has been interesting, if not informative. Thank you.
Thank you very much, Tim. This was a really astounding presentation on One Health. Your approach to AMR is truly global. I make a very quick comment because few people whose first language is not French know that UHC, when it was adopted by the UN, it was put through by a group of developing countries with France, and it was a French person who introduced it. And it was CSU, which meant universal access to sanitation. It meant universal access to wash. It's important to know because the tendency has been to transform UHC into a simple health insurance as opposed to a One Health comprehensive water, sanitation, decent healthcare systems. I was particularly impressed by your presentation on insect. But before I go on, I want to know, when do you have to leave? When do we have to? You have a few more minutes with us?
Yes, I have. I have to leave for another meeting at 10 o'clock, unfortunately, but I can then come back into the room at about 10:30. But yes, we have time.
Okay. So I have just one question. Have you looked into the story that came up, it was actually 20 years ago, on AIDS, that Stomoxys calcitrans was identified by the Max Planck Institute as a cattle fly that could transmit HIV. And they did the experiments in the laboratory between blood that was without HIV and blood would the second container of blood would be infected once flies were released in the laboratory. And so they identified it. It made big headlines at the time, and then it was completely forgotten. But I thought it was a very interesting study. I remember discussing it with the Ministry of Health of Botswana. And, Botswana being a well-developed country, but wondering why they had such high HIV rates. We also know, like in Conakry in West Africa, we have a much higher HIV rates in rural areas than in urban areas. And so this raises the question of the role of flies, which is completely a forgotten issue, to my knowledge, in HIV. I think it would be really great, Tim, if you and your team were to prepare a series of classes, courses, webinars, and of course, eventually we'll do an in-person conference on the issue of insect role in AMR transmission.
Well, thank you. Yeah, we should do that. We'll try and find the time to do that, but yes.
Yeah. So we'll show your movie, and then we will go back to the main program with Professor Yuguo Lee, and we can have more discussion with you when you come back. Okay.
Okay. Thank you. Can I just say a few things about this film? So this film was created with a group in China. And this is not meant to be an education film. It's meant to be a public awareness film. It was created by teenagers for teenagers. And so hopefully be young at heart, go with it, and hopefully enjoy it. It goes for 4 minutes and 36 seconds. Thank you.
How's the studying going?
Yeah, I've been working on COVID and pandemics, and now learning about antibiotic Armageddon.
Antibiotic what?
Antibiotic Armageddon? Basically, we're going to run out of antibiotics very soon.
Antibiotics are like those drugs that get rid of infections, right?
Yeah, that's pretty much it. Bacteria that can cause infections are increasingly resistant to all antibiotics. Some call these superbugs. We've been using these precious medicines like sweets in humans and animals.
Did somebody say superbug?
Ethan, really?
This antibiotic thing Marley was talking about does sound really disturbing.
Exactly. Just like climate change, none of us will escape this.
Ooh, really? Yet another scare story?
Listen. By 2050, it is predicted we will be back to the Dark Ages, where medicines we relied upon for so long won't be there.
2050? Who cares about 2050? This is now.
That means if you fall off your beloved motorbike, you too may have an untreatable infection and possibly die. By 2050, well over 10 million a year will die of antibiotic-resistant infections. It is way worse than COVID. It is happening right now in countries across the world. We don't have until 2050.
Come on, Marley. We're young and fit. What could go wrong?
Can't believe it. That he died like this? A simple bike accident, minor surgery, and then being eaten by an incurable infection.
We all knew it was going to happen to one of us. It was just a matter of time. We are the lucky ones. Dozens have died in my hospitals from the same drug-resistant bacteria.
You kept on warning us about antibiotic Armageddon.
How did we get this so wrong?
Good question. The evidence was all there 10 years ago, but nobody listened.
And, as usual, we were far too late.
This is just the beginning. And by 2050, it will be worse. Much worse.
Yeah, thank you. I like to thank Mrs. Grange and Wopham for the invitation. I apologize not being there on site. And I guess this will be a reflection of my personal perspective in terms of how airborne transmission can be controlled or analyzed in terms of our building ventilation and air conditioning systems. Next slide first. Next slide. So I'd like to thank a few people and students, collaborators, and so the research fund here. Next, please. It was in 2019, October, that I gave a closing plenary in the conference. Unfortunately, in the conference, I quoted Karl Marx's well-known statement, history repeats itself, the first time as tragedy and the second time as farce. Thank you. Next time. Next slide. And then it was not long, the pandemic came, so many of us reflected, and few friends wrote together editorial telling people, because that was just immediately after WHO recognized the airborne transmission, probably end of April that year, 2021. And then we thought, yeah, it's probably a indoor air crisis. It shows our indoor air not so good and might be something need to be done, and probably need new regulations, education campaigns, and new air hygiene behavior, and in particular, mandatory regulation. Next one, please. Many countries and organizations had immediate action. And please, next one, please. So this particular, I think, can be shown in the US. And by March 2022, US EPA already acted upon. And with Biden administration promised some money. And by January 2024, there was money, millions of dollars injected into school buildings. So don't worry, just stay here. So basically, I guess if we don't want repeat it, we probably need to look at the lessons behind it. I mean, what are the real lessons? It's not that quick actions will work. And if we don't want to repeat next tragedy. So in terms of air ventilation and indoor air quality, and we follow Tunga, Lydia and I joined Tunga, wrote this little review. And in particular, we think that there was a need to reduce risk infection through sufficient effective ventilation was given probably little attention. I mean, now you probably forgot that again. So there are few lessons we need to learn. Next slide. Yes, thank you. So they basically about interdisciplinary knowledge needed, and ventilation needs to go beyond just open windows. And this is basically, we believe that natural ventilation, there is a reliability problem, so mechanical ventilation is needed. And then design should focus on optimization ventilation performance. And it's not just ventilation, it's also about filtration, UVGI as a supplement, which we call the equivalent ventilation. And then we think that risk assessment tools are not immediately available. And ventilation, the last two very important, ventilation should be monitored at all time and also need to be regulated. I personally add lesson 8, which not included in the paper, and that's basically we need a science-informed policy, and this means we need to understand the science. So to me, I like to focus the three most important lessons to me. That is interdisciplinary monitoring needs and the science. In particular, I call that contagious science. So what is contagious science? Next slide. I consider contagious physics to study the interaction of results of respiratory infectious particles, and this is the new terminology from WHO, and building occupancy and occupant behavior, and the building themselves. So basically, this is about how infections spread in buildings, but which really needs more than one group of people. It cannot be done just by building ventilation people. It cannot be done just by public health. Next, please. The one particular, the debate during the pandemic was that what's exactly the transmission routes. So that's probably the most important talk I ever gave in my life was the February 24th WHO multidisciplinary workshop. And I invite people to this hypothesis and reject hypothesis if there were evidence. So basically the idea is like Einstein. So you have 3 or 4 basic observations. That is close range is very high risk. Most infections occurs indoors and very few occur outdoors by then. And then also long range occurred frequently. So in that situation, that time I concluded probably short range airborne, but now it's more like long range airborne. So with that, you can explain those 4 basic observations. And if you have such a hypothesis, the principle of science is very simple. If you have a simple hypothesis that can explain all the observed phenomenon, you have nothing to against, so that you can explain why wearing a mask works. And if you have high activity, you also have a high risk possibility, and so on. So for work like this, you really need a interdisciplinary effort, and the data collected during the pandemic helped. Next, please. With this argument, this is interesting. One of the important understanding is about short range. And this short range, by then, we already know from other studies that they are inhalation more important than so-called large droplets transmission. And very simple. You have 2 people, you have a jet going through, and this jet will entrain the air from the surroundings. And if you have outdoor air, which is clean, and then they will dilute the pollutants or whatever expired respiratory infection particles in the jet to be diluted. So the further away from the distance, and the less the probability of having been infected. For instance, with a very simple model, by then we show that if it's outside the air, and then you only have 8.3%, 8.3% of the original concentration being exposed by somebody. So interestingly, you can look into that in a room. If the ventilation is 10 liters per second per person, And then you have a similar level of exposure, 0.088, theoretically, with a lot of assumptions. But if the ventilation is reduced by 1 liter per second, then the risk increase, by 50%. So from that, you can find that the ventilation is important even for short range. I know there is existing recent study showing that not important for animals. I think they have probably a little error there in terms of what is short distance for animals. So this is very important. So please, next one. The short range becomes important. I think Mrs. Grants already mentioned WHO on April 18th, and there was a new release, a new terminology. And this terminology, basically, airborne transmission is equivalent to inhalation. There is no distance issue. You have short-range inhalation, long-range inhalation. And the traditional large droplets, we do not know how large they are. So now it's called direct deposition. The particles have to deposit on the membranes of the opposite person. And then short-range inhalation is included. And Nancy Liang and Don Newton wrote this nice summarized paper and showing, which is highlighted in red, and that's where the major changes. You have direct deposition to replace large droplets, airborne transmission and inhalation. And this actually includes both short range, as shown to the left, and the long range, as shown to the top right. So, and this to me is historical, and the Director General of WHO announced that this revised terminology must now be used by WHO and the other public health agencies across different pathogens in different settings. So there's a lot to do, and actually it's just terminology is not everything, and there are a lot of disagreement, and so this is very, very important. And what can be done? What are the future intervention? And Walsh-Rayleigh equation might offer a possibilities. You see next slide. For this, okay, thank you. So for this Walsh-Rayleigh equation, it's a amazing simple equation. I'm sorry that it should be a animation, but now to the top right, you can see this equation actually telling us two things. Very often we ignore the PI, the average concentration per probability of infection in a room, and then the number of secondary cases in a room as a function of total number of susceptible person, and order to the right, this whole thing. And this whole thing is influenced by something called quanta generation. And quanta is simply a surrogate for the dose of infectious aerosols, because we could not count how many viruses at the time, and the inhalation rate, ventilation, dilution, and so forth. So this dilution QD, and you also I call it QE later, that tells you, including not just ventilation, so and also its own settling, inactivation, maybe artificial using UVGI, and the filtration. So with this little effort, you can see that if I have this quanta is very smart invention by Wells, so that if you have 100 quanta per hour generation for 2-hour exposure, and then the inhalation rate for students sitting there 0.1 liter per second, with 30 people, that's 300 liter per second for the room, if the ventilation rate is, dilution rate is 10, and then you can use it to estimate the probability of infection, every individual, 6.4%. Multiply by 30, give you 2 people infected. If you only want 1 person to be infected or less, then the ventilation rate has to be greater than 20. So basically, if you know the quanta, everything will be known. Next slide, please. Unfortunately, to know the quanta is difficult. So in this particular restaurant, And this restaurant had 76 customers, and about 21 of them got infected. And you can see the seating. So this one is located in a large shopping center. And to the right, you have shopping area, goes into the restaurant. And then nearby, you have the bottom right, you have the kitchen. So there is a big arrow, the air goes in the kitchen. And then because the air goes into is huge, so you suck the air from downstairs up the stairs. And in downstairs, there are two zones. One is the far end to the left, and there was nobody infected there. So in the middle zone, that's where this red seats, likely the people were infected. And the index case turned out to be a senior male cleaner, and who actually stands close and probably two locations, and there was very little direct interaction with the customers. So he only collected dishes, cleaned the table after people use their lunch. It's during the lunch for a particular day. So it's strange that this person could only the people within the middle zone got infected. And using that observation, you can estimate the quanta generation is about 2,000 quanta per hour. So it's totally different from the 100 we used early on. Next, please. And you will need many outbreaks to actually obtain a profile of everybody's infection. They're all different. So unfortunately, there was not enough outbreaks to know all the data. So there was somebody proposed a viral load method. We combine the method, we produce such a profile. And this profile recently made available. And you can see this profile is log normal distribution, and probably, and then it's interesting that there are 70 only for ancestral in the first 2 years, that 30% of people were infectious. 70% of people probably not infectious, at least in Hong Kong. And that using those kind of observation, you can find this and other outbreaks. There's only 4, as we know, from before when this paper was written. So in 2 buses, 1 restaurant in Guangdong, and also a courtroom in Switzerland. So those are within the range. And this is interesting with this profile. And you can see that top 30% of people who are infectious actually follow approximately a power law. And this is really terrible, because for the top 80%, at 80%, everybody produces say about 40 quanta. If it's 99%, 2,300. So the one we just had earlier appears to be verified, at least temporarily. So with this profile, we might be able to continue to identify what will happen to this environment. At least we know that this will be very, very difficult. So proceed, next slide. And it's not just about SARS. We have other viruses, in particular influenza. And somebody proposed that they probably more airborne routes are predominant for all of them, for most of them. And remembering there are 2 things remain identical. That is the dilution ability profile of the buildings, and also the human context. We don't particularly during the pandemic, that's different. In daily life, we interact in the similar way for different diseases. So why there are differences? So it looks like, at least from what I read, it's not only viral kinetics, it's not a viral load that matters. It looks like also the transmission routes. For instance, influenza is interesting. They have a lower reproduction number. It's probably 1 to 1.8, while for Omicron, you can have around 10. But the dissipation is different. SARS-CoV-2 characterized by a lot of super spreading events. And here using K value, very small value, actually telling you is very non-homogeneous. But influenza is a little bit more homogeneous, and the K value is around 1 or larger. So this is telling us something different. Next slide, please. So very often people count the number of secondary cases per outbreak. And then you find that most of the outbreaks, there's no infection. The index case did not cause any infections. That's 0 on the horizontal index. And some of them cause many outbreak infections, like in the restaurant, it's getting to 21. So to the right, we can have a hypothesis that when you have a short range, only 2 people in a household, you might short range play an important role. But if you have long range, you have to the right, you infect many people, probably long range becomes important. And this is very, very important. And as we have learned from pandemic, because this dispersion is called over dispersion, and you go to next. And this over dispersion is characterized by super spreading events. Next slide, please. And this one, yeah. So this, you can see that somebody, Nielsen, had this very nice diagram. And to the left, you have SARS-CoV-2. What we learned is similar to SARS-CoV-1. That is a lot of super spreading events. One person infects many, and some other people don't infect anyone. Like I mentioned earlier, for ancestral, maybe 70% don't infect anybody. And the top 20% responsible for 80% of new cases. And if you target the 20% or 30%, very effective, you can stop the transmission. But if you target randomly, it's very inefficient. For influenza, opposite. They are more uniform. Everyone infects probably 3, 4, 1 or 2, and they don't cause, very seldom cause maybe more than 10 or 20 people infected. So they are more homogeneous. Why there's a difference between the two? This is amazing. So we are still in the process of studying it. Next slide, please. And I personally think this has something to do with the number of viruses, the virus particles in the droplets, infectious viruses. And as you know that at a long distance, we figure out that it's probably more infecting at origin is less than 6 micron. I mean, you can find our publication to know why. And it's a small droplets, small in volume, and based on our estimation, it's probably contain at most 1 infectious virus. So they are responded by one infectious virus particles. But at close range, you can inhale up to probably 100 micron particles. So if 100 particles and you have 1 micron, that's 100 times in radius, and then you 100 to the 3 power is 1,000,000 times in terms of volume. It contains many more possible viruses. So we find out that very likely short range inhalation involve multiple infection virus. So that little principle allow us to estimate the quanta for the long range and also the quanta in the short range. So it's very important to explain what is long range, short range works. Next, please. And this is amazing. I recently have this paper in revision. It basically says if the quantas for the long range, the quanta is important. We talked about earlier on 1,000 quanta per hour. So that long range is a fraction of the quanta at the short range. But how large is that fraction? And that fraction turned out to be 0.4 to 0.7. And it's not that you would think that the short range would have much more. This is because short range is dominated by the large droplets and they contain multiple viruses. And one, if you put everything into one droplet, which can only be inhaled by one person, right? So the quanta are not so many. And this probably explains why it's very, very important. I think it has a potential to be used to explain why there's a difference between influenza and COVID-19. And this work remains to be done. Next, please. Let's consider the same 30 people classroom as we mentioned earlier. It was 100 quota. We said that if we want one person to be infected, we have to have more than 20 liters per second per person. But our last few slides we introduced that can be potentially 2,000 quanta per hour. Next slide, please. And when you have 2,000, that's 20 times. And 20 times infection risk increase from about 3% to 73%. And there will be 22 people infected, very high risk. And you will need more than 400 liters per second per person for the dilution. And that's almost impossible in today's technology and the energy resources we have. So this is basically telling us, oh, there's a trouble. Next slide, please. Super emitters, or what we call super spreaders, actually make it impossible to achieve threshold dilution rate that could result in acceptable infection in a room of a building. Super spreader make this whole thing heterogeneity, and these elite super spreaders make this ventilation requirement is very difficult, and hence that we have to know that profile and hopefully eventually come back with a possible control strategy. Next slide, please. So this is about, it's not only about the ventilation. It can be by ventilation, filtration in yellow there, and inactivation and settling. For instance, on the two buses we studied, the ventilation rate was 1.2 or 3.4 liters per second per person. There was no concentration from filtration. There was no filters on the bus. And the bus's volume is very small, so the contribution from inactivation settling very small. And the clean air flow rate is about 2 or 3. It's very similar to ventilation. And the size also matters. We can turn that into a ventilation rate. But if you go to restaurants, and in particular this one in Guangzhou, the ventilation was only 0.9 liters per second per person. But the filtration, actually from the fine coil units used in the room, is contributing 5.5. And this is very important. And that outbreak caused some misunderstanding in the world. It looked like, oh, the ventilation is poor, and you should air conditioning responsible. Actually, air conditioning helped. Without an air conditioning, I estimated that the attack rate was much higher, because the 5.5 contributes significantly to the total clean air flow rate, 7.4. And in other spaces, similar, The air conditioning, actually, I will make these points later on, very, very important. And sometimes they actually play a positive role, because by filtration, even with the simple cooling coils. Next slide, please. So the ventilation is not the only mechanism for removal of aerosols. And this is because we have filters, we have settling, we have deactivation, we have filtration. I'm sorry, in this version, I use, around, so QE is the equivalent, QD here, deactivation. But QD I mix together early on, I took clean air. So anyway, ventilation QV is only a fraction of all the other equivalent flow rate in the system. And if you want to study outbreak, you have to know all of them. And if you want to quantify the risk, you have to know all of them. But there are some general rules. If you have a very crowded space to the bottom left, like on the bus, on the train, in the classrooms for students, then the other component is very small. So this ratio is probably around 1. If you into a spacious room, like in my office now, very spacious, I'm alone, and then this ratio is much less than 1, because setting in this room is very significant. If you have air conditioning systems, it's also much less than 1, and because air conditioning also helped. So we have to know a lot of things. And Mrs. Grounds asked me to talk about air conditioning next, please. And this is very important. I had this concept. I have never written a paper yet. And this is about hub space. If you have two rooms, A and B, you have a room in the middle, and the air from A goes to the middle. There's a hub, and that hub connects to many other rooms. And if hub space is clean, all other rooms are clean. A corridor in a quarantine hotel, in a hotel in general, a corridor in a hospital, or such an activity room in a nursing home, as shown here. And very often, at night, nobody in the activity room will turn off air conditioning, ventilation. Actually, this room turned out to be very important. Hub spaces should be well diluted. Next slide. By extending this idea of hub space, I consider ventilation systems and air conditioning system also as a hub space in a centralized system. A system serving multiple rooms. And so now on the top right, you see all this we call in professionally called air handling units. Handle the air that coming from all the rooms and then it's supplied to other rooms. And this air handling system have significant filtration ability. They filter out all the particles, and that's why you see all the particles in the air ducts. And very often in the public health investigation, they find the viruses in the air ducts. Oh, air conditioning is dangerous. That's wrong. And this is where air conditioning system have picked up them and filter them. Actually, provide some safety, provide the removal. So this you can consider the AHU and the air ducts as a hub space. And of course, some calculation is needed to go on. And I have evidence for it. Go to next slide. I spent quite a bit of time in 2020 to study this outbreak, Diamond Princess. And after the study, I eventually figured out that 1 year later, unfortunately too late, that actually there was no cross-room minimal. I cannot see any cross-room infection. And this very high-end cruise ship had 88 air handling units, and they are distributed on different parts of the ship. 1,000, 5,000, 6,000 people on the ship, and then you find out that you look at this distribution of infected individuals. They are uniform, randomly distributed everywhere. If any of the HUs are responsible, there should be cluster or something. It didn't. Actually, we have a very detailed mathematical analysis of the outbreak. We show that the room central air conditioning did not play a role. It's basically the air conditioning was a hub, and that works. I have only one final point to make. Next slide, please. According to Bing Maps and excluding China, there are 1.4 billion buildings in the world. And you assume some of the large buildings contain many rooms, and you can see how many rooms we have. So measuring ventilation or dilution in those rooms are almost impossible. And so that time we commented that probably some kind of simulation is needed. But anyway, we need to identify those spaces with poor ventilation, and we have to allow them to improve. So low-cost sensors are needed. We are working hard on this topic. We have some buildings in Hong Kong being monitored. We hope in future we can give a warning system. And in terms of monitoring, next place, it's not only the ventilation that's needed, it's also the human behavior, occupancy, and what do they do. And here you have a significant privacy issue. So we have to develop privacy-proof systems, and it's supposed to be a video here. So those are the systems in the development. Anyway, the work is still in progress. I think we cannot answer the question fully, although there are standards being developed globally. Next slide, please. My final slide is introduce what my understanding. So I think if occupancy is more than 10 people, 10 liter is good per person. And if the lower, like my office, 2 people in the office, I don't know. I think it needs to be done later. And as I mentioned earlier on, hub spaces should be well ventilated, and which I did not explain. And isolation rooms, 100 liters per second per person is very good. With low occupancy in hospitals. Thank you very much. That's the end of my talk.
Yes, sir, there is some questions. QA.
And I look forward to the talk by Professor Li Xiang-dong.
Hi, sir. Yeah, sir, please see the question, answer, and respond to them.
Where are the questions? Oh, I see some questions.
Check Q&A.
In the poll. Can you see the question you go in the poll?
Oh, well, I cannot see a question to me. I thought it was a question to Professor Tim. And Q&A.
The question you saw that is what is the most critical factor in ensure safer air conditioning system in shared space?
Oh, I think the most important question, the most important factor there, I mean, please allow me to say this, there are people inside, but actually it's the lack of dilution, whatever, and all ventilation or the size. And if it is very crowded, poorly ventilated spaces, we have this word. I finally realized we should see infection occurs in poorly ventilated and crowded spaces, and not all. So that's important to me. It's a combination of the two that makes this whole thing. I cannot see the. Oh, it's maybe somewhere here. Thank you. This is a good question, though.
Or you can take up a slide.
Oh, now I see. Yeah. It says here there's one question about what is it's called pose. Now I see. Sorry. What is the most effective method to reduce probability of infection in the classroom of 30 students? There's no most effective. If there is, we already use it. But a dilution and not too crowded. I think, yes, now people talk about using filtration, and filtration probably work best, but filtration will add to the energy cost, and it's not free. So probably we do not design buildings just for pandemic, and only during pandemic we use those systems. So I'm not for that kind of design at this moment. I hope there are better ways. At this moment, I do not know. As far as I mentioned, if there is a super spreader, like what I said, happening same in the restaurant in Hong Kong, then it's almost impossible to control infection in one particular room. But I think there are rooms for us to design for the city, for a community. So collectively, we don't let the pandemic to grow. And of course, if you really want to control effective method, mask, wearing a mask, it works in this part of the world. I know globally there are some part of the world wearing a mask is considered to be, some kind of our own right and getting us. So I actually wrote elsewhere, with mask and proper control, we know for ancestral SARS-CoV-2, it was possible to control. In this part of the world, there was no pandemic at the time. It's only the visitor came to this city and caused additional outbreaks. So I think however, for the Omicron, it was not enough. So then we got in additional trouble. Anyway, I hope I answered the question. I hope in future I can give a better answer. We are still working on the topic. Thank you.
There are
one more question. What measures can be implemented to improve air quality safety in centrally air-conditioned spaces with shared air ducts? Oh, what measures? Proper monitoring and maintenance. Thank you. More.
Professor Xiang-dong Lee, please, if you can come on, and we will have a general discussion at the end, to the extent possible, with being back. Thank you very much.
It's really nice to have opportunity to talking about our recent study. So I thinking anyway, Professor Wells have a very nice presentation regarding the flyer and other like kind of transmission pathway in the air. Also, Professor Yuguo Li just highlighted very nicely for this indoor air like emission transfer about this infectious disease. So I would just give a very quick talk within the next 20-25 minutes is regarding our recent study for the airborne transmission of antimicrobial resistance, which we have based on this for the multinational microbiological and genetic study, genome study. So you can see it's quite a collaboration with our own research group at Hong Kong PolyU, but also within Professor Jim T.G. from Michigan State University, and also including our private speaker, Tim Wells from University of Oxford. Can I have my next slide, please? I think anyway, Professor Wells already highlight how is this clinical perspective on the AMR, particularly through the last few decades, through the discovery penicillin and the golden age for using antibiotics to save millions of lives. And then reached to about early 1960s, we discover about antibiotic-resistant plasmid, which actually have this lean years, and as we have this using antibiotic, whatever in healthcare and in like agriculture like a system, so we are fighting consider about increasingly antibiotic resistance. So now we are facing about a very critical point, and regarding about health implication regarding about our food safety and other issues. Next slide, please. Anyway, I thinking about people I understand even about our ARG or AMR issues. Before this kind of like antibiotic age, we have about using antibiotic can really kill some of the harmful bacteria. But now quite a number of these bacteria we using same dose, even combination of antibiotic. So the bacteria, particularly the pathogens, still alive, causing our health issue. You can see whatever about the currently we have directly from AMR, we have almost 1.3 million people premature deaths. Compare if we haven't find the right kind of whatever method to control. So our kind of one study estimate, it could be reached to about 10 million people by 2050. This even about equivalent. Currently, we have this cancer, various different cancer in the world per year. My next slide, please. So I just want to using to highlight the two regions where in the following I'm going to talking about. One is a particular AMR threat for the global public health issue. One definitely within about this Asian Pacific region, majorly through about the east, like this West Pacific coast or into Southeast Asia. Another one is about African continent. So you can see the largest probably predicted like health threat from AMR occurred in this two most populated region, and also with facing about this tropical, subtropical region climate. Next slide, please. Anyway, I'm not repeated too much on this because we do have this development antimicrobial agent through about fighting through this antimicrobial resistant AMR issue. Now this kind of battle actually come forth, and whatever we needed to looking even a new novel and antibiotic like whatever drug and other issue, but in the same time we have the thinking about some of these past or unused antibiotic losing its kind of effect in healthcare use or in other agriculture applications. Next slide, please. One of the case I think in particular for this today's topic, we you can see from the slides here, not only for about this kind of a clinic like in hospital acquired, but much widely so far is considered is how environmental kind of like acquired like AMR issue through whatever from various environmental medium. Like through our water, food, but also in environmental factor, including the air inhalation we have. Professor Yuguo Li already talking about this indoor air quality, but my study is more considered with ambient outdoor environment issues. Okay, next slide, please. So anyway, there's an issue considered. There are quite a different mechanisms behind this kind of a horizontal gene transfer (HGT) consider spread about AMR through whatever consider about a different plasmid acquired through about conjugation or through some of this transformation. And through live or dead kind of like a cell into about a particular like bacteria itself. Okay, next slide, please. So I just want to highlight one issues because usually we have done quite in the past, the last 2 or 3 decades, we have done many of these environmental medium, including the natural environment, like we have these soils, sediments, and the river water. And also in the left-hand side figure, you can see also we have many study into the engineering system. So that's including our drinking water pipe, our wastewater treatment plant, and also our kind of a wastewater treatment sludge. There are also definitely from our human and animal like system or excretors consider our gut microbial and others issues. But you can see in the left-hand figure, the red 2 bars there is our human atmospheric interface. So the one is regarding our PM 2.5, like the very small particle we inhalate through the air, whatever for the ambient air quality or even indoor, but also consider with inhalation breath condensate, where they can still be a major carrier of these lethal pathogens and also ARGs, antibiotic resistant genes. Okay, so my next slide, please. After realize the air can be an important component in our overall environmental like exposure, so we can really have a quantify through our own study, consider about how this like our city hotspot as a potential source for emission. You can see definitely we are looking about this wastewater treatment plant. It's hot breeding ground for the ARG like antibiotic resistant genes. But also we are looking about in our hospital, consider inpatient ward consider about outpatient like clinical area. So they all can contribute significantly for about the whole urban air, the air like in a very whatever outside and ambient like atmosphere. Next slide, please. So the key question, particularly through our last decade study, is how about surrounding airborne transmission for AMR? We need to focus our attention scientifically. Just quickly highlight some of the point here. So there's aeration and source emission from whatever from our urban. I just mentioned in the last slide, wastewater treatment plant, hospital. But there are many others kind of source, like even our solid waste, landfill, others. So in that particular point, we have our study probably about 2 years ago. We have built a global like airborne bacteria community map in the world through our own like air PM sample, through about other kind of good like literature data. We compile this the first like airborne bacteria community map, like on a global scale. Next one, please. So I just want to quote one of a recent study, also in the PNNS, is our live in ARG carrying bacteria, even after they travel like a long range in kind of from Europe to America. So they still can actually have this live bacteria, can really, you can culture them to see about they are really still have about this kind of like whatever we can infect like in condition if we have inhalation this pathogen through about this contaminated air. Okay, next slide, please. Okay, so in the current study I'm talking about today is we have generating a global airborne metagenomic database through our own like air PM samples. We collected quite a number. You can see from the map is quite a number of the red dots there, but we also rely on some of this other literature data, try to combine all this kind of whatever possible high quality like data set we can incorporate as a kind of the global like airborne metagenomic like a data set. Okay, next slide, please. Okay, I just want to highlight as a study, we also needed to focus on this kind of whatever the very populated urban area. You can see like even the city landscape in Hong Kong, but it will also cover a bit of this background side where kind of like a less human activity touch area. But also we compare both the land and ocean system to see how about both this bacteria community and also ARG like a profile difference. Next slide, please. Okay, but anyway, I'm not going too much in detail. Some of you can actually refer our formal previous publication because we need about the PM sample for this whatever about the DNA extraction, about the qPCR like kind of quantification. And then we have this library generation for about bioinformatic, particular for metagenomic side. And then about all the data analysis, sometimes taking about several months to analyze this kind of statistic and correlation side. Anyway, next slide, please. Okay. So I skip on this. If you need further information, I actually our next publication will detail all this. This means how about our air sample collection. We have a totally around about 758 sample. We have also considered about this DNA extraction, or this kind of metagenomic analysis, consider about whatever literature data we have through about our quality assessment, then getting about this raw data into a full global data set. You can see cover about area we have through about East Asia, the Pacific, into the Europe and the Middle East, North American, about this South American, and also about Sub-Saharan African data set. Next slide, please. So I aware a bit of time. I have to speed up for about some of the result we have. You can see currently we can all this kind of metagenomic data, we can identify there's over 700 like ARG subtype. So that's kind of involved with 24 different major drug classes, which actually can detect in the global air samples, the ambient like air samples. So they can be quite a number of them through about this significant number of this ARG. But if we putting about the core ARG, I mean, although there are a number, but they can dominate relative abundance around about 60%. So you even can see about how much the risk ranking for this core airborne ARGs, significantly the core sample have a kind of a relative about this risk 1, risk 2, and risk 3, more than half of their population in in the air. Next slide, please. Okay, I thinking you know about in the global skill study, there are many of the past study regarding about whatever this kind of a topsoil. We can find a very significant database and also ocean system. And we compare our data within about current available ocean system and topsoil system, agriculture system. So you can see the air one, definitely they have the common species, which actually unify this kind of like all three ecosystem, surface, earth ecosystem. But there's many other unique system. So you can see the air system really have a unique than any other like topsoil and ocean system. Even we putting on this kind of like a co-ARG side. So air still have this unique kind of species or about this in the atmospheric itself. So in other way, so the air really have this kind of interaction within our surface like ocean and with our kind of a land system as well. So that's why they have also a very dynamic and changeable like system. Not like the soil can be relatively stable for about whatever for natural soil, agriculture soil, or even the ocean, consider with deep ocean, consider with estuarial system. Next slide, please. Okay, if we compare either about this different region, we can see there's quite a bit of comparison. Consider some of this our remember the region using WHO data set projection about O'Neill report. This kind of African and also East Asia and the Pacific can still is the two regions have dominate within about these health issues. But in our ambient air, they also kind of correlating well with that prediction, because you can see about how there is a kind of a issue. And another one is compare our like in the middle of the diagram, you can see compare within the rural and the pristine background side, the urban, suburban side have a much higher relative abundance of this kind of ARG anabolic resonance genes. So they also reflect quite a different connection between this rural area compared with the urban and the city side. Next slide, please. Okay, if we put in a little bit, consider our using energy relative abundance compared with the current health expenditure for each of the whatever WHO country and the region statistic, we can find quite an interesting pattern here. So the country who spend quite a lot of this health expenditure or consider have there's a gross domestic GDP type per capita. So they have a relative kind of lower for ARG relative abundance in the ambient air. So in other words, so the well-controlled, better like healthcare system and the AMR issue in the air, at least the ambient air reflection about there's how they manage, how they actually the issue of public health threat less compared with other countries. Okay, next slide, please. Okay, here is a different ARG composition. Particularly, we compare about this city side and with the rural area. You can see the city side, the purple underneath of the one is the anthropogenic enriched antibiotic-resistant gene in the human and aquatic and terrestrial environment, showing very high abundance in the urban air than in the rural area. This very significantly, we can see about our human impact through our ambient air using about this AMR and antibiotic-resistant genes. Next slide, please. Okay, so another way, how about this potential anthropogenic correlation between airborne AR antibiotic-resistant gene abundance, compare even how we use antibiotic resistance in our whatever average per country consumption. You also can see there's quite a good correlation into our touch recycling, beta-lactam use within about this relative ambient air detect. How about this kind of antibiotic resistant gene in the issue? Okay, if you focus on this left-hand bottom one, so if we're going to use analyze which is the control factor for the ambient air antibiotic resistant genes, so the source and the socioeconomic factor contribute over 50%. So then the geographic location, wherever they are region subtropical, temperate or other regions, they have a contribute around about 18%. So the last issue consider is controlled by meteorological condition, like relative humidity or whatever air quality, PM2.5 pollution and ozones and others. Next slide, please. Okay, so another particular issue is not only for the bacteria AMR, but also how much of them can really have these pathogenic genic issues. For example, they are be carried this AMR by pathogen, which can cause significantly a disease or infect our respiratory tract and causing about whatever other health issue. So in this case, we really have around about this significantly this kind of this metagenomic assembly genome was really have about this violent factor genes HVF, which have a particular in the city much higher than about this rural area. Next slide, please. Okay, so that's one we have putting our normally exposure assessment, using one person's relative adult inhalation about this air amount compare about this rural area and urban. So the population pathogen in the entire bacteria community was higher definitely in the urban area, as we have already saw them in the relative ARG abundance, but it also have a high about the pathogen involved. So that's why, like Professor Yuguo mentioned, in a very confined, even indoor shared space, we'd be better have a more protection and know about the mask or whatever. Okay, so the high exposure risk in urban area regarding airborne pathogen, and also consider about the AMR, the antibiotic resistant gene. Next slide, please. Okay, we also just mentioned about this consider with the source, consider with kind of anthropogenic like activities. You can see we have looking about this atmospheric temperature, this nitrogen oxide, sulfur dioxide, consider PM 2.5. Also consider how much about population density, consider about how this kind of whatever this terrestrial industry compare within other agriculture others. You can see there's many factors interrelated, but majorly the population density play a very important role compare our like whatever human inhalation, exhalation exchange with our ambient air. Next one, please. So putting in this clinical relevance, there's a very interesting finding. We have using this antibiotic resistant rate for clinical isolate, like hospital reported to WHO data, in a global comparison to see how many countries, whatever they reported, there is a clinical isolate. Compare is our relative, very close, approximate location in our finding for this relative abundance for antibiotic ARG in the ambient air. So you can see in the left-hand side global data. So there is a kind of a small curve, but then regarding to increase for that. We further zoom in for particular China upon like a few cities. They also can see about this linear correlation between this isolate clinical like scotitus areas MAG in the urban air was found to carry about this really pathogenic like issue here through about air PM 2.5. Next one, please. Okay, so we putting further into community level identification, how much about horizontal transfer ARG can happen. So you can see how about urban side quite a double about this rural side. Consider they carry the higher risk 1, risk 2, like pathogens through about this WHO like recommendation list. So that means urban air tending to harbor a large proportion of horizontal gene transfer ARG among the predicted HGTs, like horizontal gene transfer. Next one, please. Okay, I thinking almost my time up. I just want a very quick summary here, like as your taking home message. I hope actually the study give you about really some of the preliminary data. Consider our relative abundance for airborne ARG into a global scale. Anyway, you can see the high kind of abundance in the African continent and the East Asia and the Pacific region. And also there's a major way considered with a social contribution, human activity can play a very dominant role in shaping the airborne ARG abundance within climate and the geographic factor. So the urban air also characterized within a high risk, the ARG. That's why we really need kind of refine our indoor air quality, consider protecting about public health. Anyway, there's interestingly, there's a kind of a strong correlation between ARG relative abundance with the airborne like Staphylococcus aureus carrying about this massa genes and within about corresponding find in the clinical isolate. So hopefully it proves that ambient air monitoring can even indicate our general public health threat in the future. Anyway, thank you very much. I thinking anyway, can I have my last slides acknowledging my co-author, including Professor Tim Walsh. Yeah, here is anyway quite on my group in the first row, and Dr. Jiawen Carmen Xie and Candice Zhao, and also Tang Tian He, and also Nathaniel Jin, and also Yang Wu, and also Zehua Yan. Anyway, Professor Tim, Professor Jim TG, and Professor Tim Wells, and give us quite a very good advice, and also as a joint co-author for the study. Thank you very much.
Sir, there is some Q&A. Can you check?
We'll take some questions for the overall presentation. We thank you very, very much. I think it's extremely thorough. If we take the three presentations together, it's a most in-depth scientific presentation on what the situation is, and it actually calls for more development, and I would think more classes and webinars to make it accessible to the policymakers, so that you, the scientific community working on those issues, can tell to policymakers what they should do to build those air conditioning system, kind of a mask they should put on. So we'll take respond to a few questions.
Okay, I saw quite a number of questions here. I try my best to see how do bacteria adapt to changing environment, and what the role does this adaptability play in their survival and evaluation. Very good question. I thinking anyway, there are many of these bacteria are much more resistant, or much more kind of whatever through their harsh environment. We normally know the air compared with the soil and ocean water are quite a kind of like a harsh environment, because there's a limited nutrition supply, but also kind of a temperature change between day and night. But there are some of these bacteria can really survive through about this the harsh environment as about whatever in the atmospheric environment. So that's why I have using this PNAS paper, which actually through the Europe and North American study, which actually cross-continent transport, there are still culturable bacteria and pathogen existing lively. So in a word, our natural selection system already ground this bacteria whatever cell and can survive, and really can using the air as a mean for transform in the long range for pathogen and infected this virus or other things. So that's being scientifically proved. And but we still need to understanding the mechanisms involved, how they actually adapt about a new air from the whatever, from water, from soil space, from the plant or others. So that's kind of the issue here. Okay, so the second question is, how do beneficial bacteria in human microbiome contribute to health and prevention? That's a good point. I thinking about we already have where kind of many of the medical study already putting on our gut microbiome. So there's a kind of a well evidenced study. So our gut microbial health control quite a number of disease in human beings. Whatever, if we maintain a much health gut microbiome, which can actually eliminate quite a number of the digestive or other disease. So that's for sure. I thinking, but anyway, we still not very much regarding our respiratory and lung kind of a microbial calculation. So I hope we, any of our audience or in the medical field or in the biological field can actually putting into this kind of a really interesting frontier research. So whatever possible collaboration or whatever others. So this definitely is a very important new area to go forward. Okay, what are the primary factor contribute to the rise and AMR, and how can they be addressed on a global scale? I think in this question probably are leaving for Professor Walsh, if team around here.
I think Professor Walsh is not back with us yet.
Okay. I will try in my kind of way to consider is, I thinking the primary factor consider about is our current treatment system. So I still actually consider prevention is a better medicine than anyway whatever medicine ourselves. So we need understanding who contribute towards this environmental factor. I thinking team already laid down a great example. Even fly can transfer into within like hospital ward, and also can many of these other disease. So I definitely, if we cutting off the emission source at a spot, we can really improve significantly for our kind of like part of this issue here. Okay.
We have a question from somebody from South Africa. You want to come in?
Yes.
Go ahead. Go ahead.
Hi there. It's Greg from South Africa. I was quite interested to see that in one of your slides you highlighted some work that you are collaborating on in South Africa. Could you maybe just expand on that a bit, if any work you're doing there?
Okay. Yeah, I thinking that's the South African data we have obtained from literature is not our own kind of a sample analysis, but we have checking about this issue which rely on this kind of really good quality from sampling into about this bioinformatic analysis. So, but I must say, so far we have only limited locations for about South African study. So we still want to incorporate more database or more data into about a whole global study. So that's already, but there's only, I would say, is an early indication for about the issue both we facing in East Asia and the Pacific region, and the Pacific African case study as well, because that's correlated within about the owning report, this kind of two region are significantly. So our air data really indicate, although we have a limited size for about this data, but is just the early sign. It can really reflect in the ambient air situation.
Thank you. Thanks.
Thank you. I think Yuguo, there's some question for you for air conditioning system. If you're still around.
Yeah, I am.
Yeah.
Let me see.
There's one question asked is what measures can be implemented to improve air quality in central air conditioning space with a shared air duct.
I mean, there are many ways to improve air quality in centralized air conditioning. In this part of the world, I think we do better maintenance, and of course, the system itself, it depends very much where you are. I mean, probably on campus, as far as I know, that we actually have a good monitoring of CO2 levels in all the classrooms. So there's dedicated engineers looking after your BIM system, building management, energy management systems. So I mean, in terms of the system itself, it really needs regular maintenance and checking. So, but we all know that building systems are so complicated that even a very well designed and operated system, we often find the data are.
You never get for me then.
Thank you. It's a good one. Unfortunately, very difficult to give a general answer.
Put both on you. See which one you come.
I think there's quite a number of questions. I don't think we have time to answer one by one. But anyway, I just want to one solve question regarding aerosolization from wastewater treatment plant. So that's a very good question. We have currently have the sampling scheme right now. We have a study about different like wastewater treatment wastewater treatment tank consider about this condition within this whatever relative humidity, like temperature, and also this biological chemical treatment, like a process, to see how we can quantify this kind of aeration like a process, how we can probably advise after our study to see what we need to cover about some of this kind of reaction tank, or some of the sludge separation from efferent and issue to really reduce this kind of aeration from this water bubble or from this sludge or from other. That's definitely a very interesting and good question there. Yeah. So yeah, there are many other kind of environmental factor can contribute towards about all this whatever kind of environmental factor can looking this climate and this kind of meteorological condition shaping the airborne ARG dynamics. That's true. And but the point is it depends about the source profile. Consider about how this antibiotic resistant gene was carried by what type of the pathogen. And we also find another interesting point is like a bacteria and this phage interaction, which can actually really in same pattern as our flu season from whatever if you in the North Hemisphere you know about from January to March, there's a peak flu season. And anyway, I think Yuguo already expert in kind of infectious disease. But for our ambient air, so that's kind of also the linkage between the ambient like bacteria and the phage interaction within about the peak of the flu.
Hello, hi sir. I have a question.
Please go ahead.
Yeah, with airborne methicillin-resistant Staphylococcus aureus MRSA linked to clinical isolates, how should healthcare facilities adapt their infection control protocols to address airborne threats?
Very good question. I thinking number one is a kind of like the ambient like air sample in a kind of whatever in a couple of site in within the city. But this kind of isolate, like a clinical isolate, is actually from data from a WHO report. So there's definitely from our data, we can see there's a kind of statistical correlation. But where about this directly from about hospital inward or from other, like as I mentioned, from a wastewater treatment plant or from other kind of possible solid waste, like our food waste treatment facility or other, that's still a possibility. So I don't think there's only one single is actually only source from a hospital. But anyway, I thinking there's a quite an interesting way. So how about from the hospital emission source, can we cutting off this kind of like emission to really control at the source, particularly our healthcare professional and how they are actually being better protect and consider about all this AMR issue or other long-term health kind of a benefit. We can still have a way, but anyway, I think Yuguo probably have a better idea for about this kind of indoor control for this infectious disease.
Okay, sir. Thank you for the information.
Thank you.
Thank you very much, everybody. I looked through all the webinars that advertised about in relation to AMR, and I must say we were the only one talking with the theme of airborne. So I think this is very important. I think I see. Okay, you can see it. You can have a replay of this webinar on the portal. It's called portalexpert1health.org. And you'll see you can navigate the settings section, I'm told, to get the webinar certificate and generate certificate from there. Okay. So I want to say that I think this is very important. It should be the beginning of all. And I wanted to ask a question to you three. Don't you think that it would be important to make a presentation or draft a proposal for policymakers on this issue? Because I think that hospitals are not conscious of it. Construction companies not aware of it. AC companies not looking at it, and there's an enormous improvement that could be made if the public body, the decision makers, were better informed on this issue. What's your thoughts on this?
Definitely a great idea, and we can actually anyway, and if a team and also Yuguo can leading effort, we definitely be happy to write a viewpoint article to particular for general public and also for policy makers, because this a great issue considered public health. So we be happy to share our study result and to whatever to inform the policymaker, but also to like inform public, consider how to protect ourselves, even a healthcare professional in a kind of a special setting. I thinking definitely. Yuguo, you have any other point you want to share with us?
I mean, not really. You covered very well. I'm not less familiar with ART, and I think whatever we do, it has to be realized in practice and somehow. So the proposal is a great one, and that is probably is same to me in a hospital environment. It's not just ARG, it's not just infection. There's many other issues, and I think somebody mentioned in the question early on. So yes, I would be very happy to join your effort if you think there's something can be done. And yeah, I believe policymakers, effectively at the end, is these policymakers that will play a role in making any changes to this work. Thank you.
Thank everybody. It was a really great, very informative webinar. And I'm very delighted to have heard you all, very honored to have the three of you agree to participate. Again, people will be able to see a replay for those who could not, because I had complaints from the US from really high-level professors. Some of them are co-authors of your study. And they said, we're in the US, we cannot listen to it because of the time frame. So we'll try to arrange to also have webinars with the US time frame. I'm an American myself, though I'm in Dubai recently. So we hope to see you all for the next in-person conference. But in the meantime, let's keep in touch and see how we can develop the kind of courses, both for people in microbiology, people doing advanced research, as well as for policymakers. And again, I thank you very much. I thought it was a tremendous session. I don't know if Raul maybe wants to put the movie that Tim loves so much, see if it works. I don't think it will work that well, but we have disseminated it everywhere. So we'll send you the link in case you haven't seen it, and send it to your kids and your grandchildren and everything yourself. Thank you very much.
Thank you, Gareth, for organizing this. I'm sorry, and we cannot answer every single question, but just email us, Yuguo and myself, and also Professor Tim Wells as well. We're happy to to follow up with your inquiry and the collaboration and others. Thank you very much.
Thank you.
Thank you.
Bye.
Thank you. All the best.
Bye.